Let's investigate Grover's search algorithm. First, let's understand this geometric visualization. We can identify vectors living in a two-dimensional plane. All of these vectors are normalized, so we can think of them as having a length of 1. We can identify a vertical axis and a horizontal axis, and these two axes are perpendicular to each other. So all of these vectors are geometric representations of quantum states which live in a Hilbert space. Let's label these vectors. The vector that lies along the vertical axis, we're going to call that omega. So omega, I'm writing inside of a ket. This is Dirac notation for a quantum state. This omega is the state we are searching for. We're going to use Grover's search algorithm to find this state. And what do we mean by finding the state? We're going to maximize the probability of measuring this state. And we're going to do that by iteratively applying unitary transformations. Let's also label this state along the horizontal axis. So geometrically, this is perpendicular. And we can also say that in the language of quantum mechanics, it is orthogonal. It is an orthogonal state. And I'm going to denote that by omega with a little perpendicular sign over here. So this means perpendicular or orthogonal. And orthogonality means that the inner product of these states is 0. Let's also label this state. This state is S. And it's S because of the word superposition. We have a uniform superposition of all of the computational basis states. That is what S is. And notice that the angle from the horizontal axis, so in between S and this omega perpendicular, this angle is theta on 2. And if we go theta on 2 in the opposite direction, we reflect S across the horizontal axis. So this reflection we can do by applying a unitary operator, which I'm going to call U sub omega. And when that acts on this vector S, we get the vector at the bottom, which is just a reflected version of S. And notice that if we reflect over the S-axis, then we get up to this vector. And we can do that by applying another unitary transformation, which I'm going to call U sub S. And this reflects over the axis that goes through this vector S. And then we have U omega and S. So you can see we begin at S, we reflect over the horizontal axis by applying U sub omega, and then we reflect over the S axis, and that gives us this final state over here. And if we do this procedure iteratively, then we will move towards the vertical axis. So there is an integer number of times that we apply these operators to the state S, and that gets us very close to the state omega. And this is a geometric intuition for how Grover's search algorithm works. So we iteratively apply these unitary operators, and that maximizes the probability of measuring this state omega. And what is the probability? Well, the probability is the absolute value squared of the inner product of the state with this state over here. So we're looking for the probability of measuring omega. So we want to reduce the angle of the state of the system and this vertical axis. We want to move it up towards over here. So we've seen a geometric visualization, but now let's write down a quantum circuit diagram. And then let's write down specific definitions for these unitary operators. So first, we're going to initialize the system. This system is going to consist of little n qubits. So I'm going to write this as little n. So little n is the number of qubits. And we're going to take that little n, and we're going to use that to construct big N. And big N is the dimension of the Hilbert space. So this is defined as 2 to the power of little n. So this is the number of qubits in our register, and this big N is the dimension of the Hilbert space. Now you might be thinking, if this is some large number over here, how can we represent this as a plane? Well, this plane over here is not the entire Hilbert space, but it is a geometric section in this Hilbert space. So this is just a tool to visualize part of the Hilbert space. It's states that live in the Hilbert space, and we're just visualizing them in a 2D plane. So now let's consider some qubits, and we're going to start them off in the state 0. So all of our qubits are going to be initialized in the computational basis state labeled as 0. And we have n of these qubits, and I'm going to use a shorthand notation. So I'm going to use a little line, and then I'm going to write little n. And that tells us we have n copies of this. So this saves us from writing many of these lines and many copies of these states. So the next step is to apply the Hadamard to each of these qubits. And we can denote that by h with a little tensor product and then little n up here. So that's the Hadamard gate. And after we do that, we're going to apply the unitary transformation denoted by u omega. So we have u omega. And after u omega, we're going to apply us. So just like in our geometric visualization, first we apply u omega, and then we apply us. But sometimes it's not enough to just apply it once. We have to apply it many times. We have to apply it iteratively. Because in general, this s might be really close to the horizontal axis. So we're going to need to reapply this many times to get very close to the vertical axis. So what I'm going to do is I'll put some brackets around this, and we're going to apply this r times. So that's r applications of this combination of unitary operators. And then after that, we're going to perform a measurement of all the qubits. So this is the symbol for measurement. And then the result of a measurement is going to give us bits. So this double line means that we're dealing with bits. Now, if we were to draw this diagram out in full, we would have little n lines going through here. And on each of those lines, we would have Hadamard operators acting on all the qubits. And the input for u omega would be little n of these little lines. And over here, we would have little n lines. And all the way down over here, we would have many copies of this measurement operator. So this measurement takes in a qubit and it spits out a classical bit. And we can read that as a 0 or a 1. And then when we have all of the measurements of the qubits, we can consider that as the outcome of our experiment. And what we're hoping for is the outcome that corresponds to omega. That's what we're trying to search for using this search algorithm. So now that we have this quantum circuit diagram and this geometric visualization, let's write down some specific information about the operators and the states. So what I want to do is identify important parts of this procedure. So over here, we're starting with the initialization of all the qubits in the 0 state. And at this point over here, draw a little dotted line. At this point, we have the state S. So this is S. That's the same S that we're dealing with over here. And what about over here? After we've iteratively applied those unitary operators, what do we have? Well, we have the state that looks like this. We're going to apply us, u omega, r times. So this is the number of iterations or number of repetitions, and we're going to act on s. And so this is going to be the state of the system before we perform all of the measurements. So the measurement comes after this part. So these are the key important stages in this procedure. The reason we apply these Hadamards is to take this initialized form and turn it into a uniform superposition. So let's write down what is going on with this S. So S, what is it equal to? Well, S is the result of applying this multi-qubit Hadamard, which I'm writing as this tensor product, little n times, and we're applying that on the state 0, n. So this is shorthand notation for little n copies of 0. So all of these qubits are initialized in the 0 state. And then we act with a Hadamard on all of them, and we can write that as 1 over square root of big N, right? This is the dimension of the Hilbert space, which is the same as 2 to the little n, times the sum from x equals 0 up to big N minus 1. And all of these x's are the computational basis states. So we can label them with numbers, starting from 0 all the way up to big N minus 1. Another way we can write this is this coefficient can be expressed as 2 to the minus little n over 2. The minus sign is because of the reciprocal. The power of 1/2 is because we have a square root. And this 2 to the little n is the definition of big N. And then this sum, we can express the sum over x as an element of all of these strings of zeros and ones which have a length little n. So this is another way to express all the combinations. And I'm going to put x over here. So this is what we're dealing with. This is the state S. It's a uniform superposition of all of the computational basis states. And you can label the computational basis states with numbers starting from 0 going up to big N minus 1, or you can label them with binary numbers. So these are strings of zeros and ones that have a length of little n. And if we were dealing with 2 qubits, we would just have zeros and ones. So we would have 4 options. We would have 0, 0, 0, 1, 1, 0, and 1, 1. And that would be our computational basis for a 2-qubit system. But this generalizes to n-qubit systems. So this includes all of the computational basis states, and they all have the same coefficient. That means they all have an equal probability of being measured. What about this omega perpendicular? So this state that's orthogonal to omega. Well, omega is one of these states. One of these x's is omega. So if we want to construct a state that's perpendicular, what we have to do is remove omega. So omega perpendicular is the same as this, but we have to just remove that omega. And we also have to renormalize. So instead of big N, we're going to have big N minus 1 in this normalization coefficient. And then we're going to sum over all values of x that are not equal to omega. So we just exclude that omega. And otherwise, it's the same state. So we're just ignoring that one special state that we're looking for. And if you take the inner product of omega with this omega orthogonal, you're going to get 0 because you won't be able to find omega in here. And that means you're just going to get an inner product of 0 for all of the terms. That's because all of these states are orthogonal to omega. This is the computational basis. It's an orthonormal basis. Now let's write some important observations about S. So let's express S in some interesting ways. So first, we can apply projectors to S. We can project S in the vertical and the horizontal direction. So first, let's write down the horizontal part. So we have omega orthogonal, and this is a projector that I'm constructing. It's a Ket-Bra combination, and it's acting on S. And then we also have, so this is the horizontal projector. We need the vertical projector, which consists of omega in a Ket-Bra combination. So when we act with these projectors, what we can identify is an inner product over here and another inner product. And these inner products can be written in terms of these angles over here. So let's write that over here. We're going to have cosine of theta on 2. So that's this theta on 2, right? This is the angle. The cosine of theta on 2, that's the horizontal component, and the vertical component is sine of theta on 2. So I'll write omega orthogonal, and then we're going to have sine of theta on 2, and then omega. So here we have a horizontal component and a vertical component. And another way we can write this is in terms of big N. We can write this as the square root of 1 minus 1 on big N times the horizontal basis vector. And then the coefficient of the vertical basis vector is 1 on the square root of n. Let's reason as to why this is the case. Well, if we take the inner product of omega with S, so we take this omega and we take the inner product with this combination over here, we're going to get 0 for all of the terms that are not equal to omega. But omega is somewhere in this sum. And when we take the inner product of omega with itself, we're going to get 1. It's a normalized vector. And that 1 is going to multiply the coefficient, which is 1 over the square root of big N. So that explains this term over here. This is the same as sine of theta on 2, and it's also the same as this inner product. So we have 3 different ways to express the state S using this projection of a horizontal part and a vertical part. And we also have this definition of S as a uniform superposition of all the computational basis states. Now that we have S, let's construct U sub S. So U sub S is equal to 2 times the projector formed from S, so that's a Ket-Bra combination of S, minus the identity operator. And this is a way of expressing reflection over the S-axis. So what is very special about this is we can also write this as a sandwich between Hadamards. So we can take the Hadamard operator, but we need to apply it to all little n qubits, and we can sandwich this combination. So we have 0n, 0n minus the identity, and then we need another Hadamard on this side. So this is an alternative way to express U sub S. So this U sub S over here, we can unpack that as this operator sandwiched between a collection of Hadamards on both sides. So we can take this combination and we can sandwich another operator to form U sub S. And what does this actually do? Well, if you consider this identity operator, this is minus the identity. So we have a minus sign on all of the terms. We're introducing a minus sign on all of the terms except the first term. That's the term that corresponds to all the zeros. This sign gets flipped. We have 2 minus 1, which is plus 1. So we have a plus 1 on the term that has all zeros. So that's at the top of the matrix, the top left of the matrix. And all the other diagonal entries are going to have a minus sign. So what does this look like for some general x? So if we act with US on some general x, one of these computational basis states, what is that going to look like? We're going to have 2 copies of the projector acting on x, and then we're going to have minus the identity, and that's just minus x. So we can interpret this as an inner product, and that's a number. So we have S scaled by 2 times this inner product, and that's lying on the S-axis, and then we subtract off x. And this operation is the same as reflecting over the S-axis. For the special case that x is equal to S, so imagine we substitute S over here, then we're going to have an inner product of S with itself, which is 1. So this is just going to be 1, and this is going to be S. So we have 2 copies of S minus S, that's S. So reflecting S over itself has no effect. It's the same as the identity. So now we have a definition for U sub S, and we have an alternative definition for U sub S as well, in terms of these Hadamard sandwiches, and we've seen how it acts on a state X. So now let's have a look at U sub omega. So U sub omega can be defined as the identity operator minus 2 times the projector formed with the state omega. So what does this do? Well, it's the identity minus this state over here, this projector. So it flips the sign just for this state. You could think of it as labeling the state omega. So the state we're searching for, it labels it. And what does it do geometrically? Well, it negates the component along the vertical axis. So you can see this component over here gets flipped. So we go from this plus value to a minus value. And that's because of this part of the term. Otherwise, it's the identity operator. So that's the only way that it differs from the identity. We can write this as a matrix representation. So what is the matrix representation? It's a diagonal matrix, and the entries are minus 1 to some f of 0, minus 1 to f of 1, and we're going to go dot, 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 all the way up to minus 1 and f of big N minus 1. So this is what we're dealing with over here. And what is this function f? Well, I'll write this out explicitly. F is a function that takes in inputs from 0, 1, all the way to big N minus 1, and it maps these inputs to either 0 or 1. So if it's 0, then we're raising minus 1 to the power of 0, so we're going to get 1. But if it's 1, then we're raising minus 1 to the power of 1, and that gives minus 1. So it flips the sign. And what we need to do is define this function so that it only gives a 1 when we have the input associated with omega. So that's how we target this omega. And this format over here, this is sometimes referred to as a oracle. And this oracle gives us information about which state we're looking for. So we have some kind of database which we can translate into a quantum oracle, and that's going to allow us to label which state is omega. And we're going to use Grover's search algorithm to search for that omega. Let's see how this u omega acts on an arbitrary state x. So u omega acting on the state x, we can write that as minus 1 to the power of f of x as the coefficient of x. So that is another way of writing this matrix representation. So if we take some state x, it's the same when we act with this unitary operator as minus 1 to the power of f of x. So this has two options. So we can write this as a piecewise function. We're either going to get plus x or we're going to get minus x. We're going to get plus if x is not equal to omega. So if it's not the target that we're looking for, then we're just going to have f of x equals 0. But if it is the target, then we're going to have x equals omega. And then we need a minus sign. So that means f of x has to equal 1. So the function turns on when x is equal to omega. It's equal to the target, and then we flip the sign. So that's what u omega is doing. It's identifying which of these states is omega. And us is doing this reflection. And collectively, if you apply both of them together, they are doing a Grover iteration. So they are moving the state s closer to the vertical axis. And it's by an angle theta. So this theta over here is the same theta that appears over here. So the net process of applying one iteration is a rotation by the angle theta. And let's write down something very important concerning the inner product. If we examine the inner product of omega with the state s, we can read off over here that that is equal to 1 over the square root of big N. So we found that out earlier in the video. And we also know that this is equal to sine of theta on 2. And in the approximation, where n is really, really big, this is going to be a small angle. So that means that s is going to be very, very close to the horizontal axis. So we can approximate this with the first term for the Taylor series of the sine function. And that's just going to be theta on 2. And this only works if n is much, much bigger than 1. So this over here works for n much, much bigger than 1. That's an approximation. Now, what we want to do is maximize the probability of measuring omega. So we need to write down some probabilities. Let's try and understand these probabilities. So the probability of measuring omega, given r iterations of this Grover algorithm, that's going to be the inner product of omega with this final state. The final state has the form us u omega applied r times to the state s. And because it's a probability, we have to take the absolute value squared of this inner product. Let's take a special case, the probability of measuring omega given 0 iterations of r. That's the inner product of omega with s. And we have to take the absolute value squared to get a probability. So if we apply this 0 times, we don't apply this at all. So we can ignore this part of the circuit. We just prepare the state, we initialize all the qubits, and then we apply the Hadamard's, and that gives us the uniform superposition. So what's the probability? Well, we can identify this equation over here, and we see that this is equal to 1 over big N. It's also equal to sine squared of theta on 2. That's from this relationship. And that's the case if we don't apply it at all. But if we apply it r times, we're going to get sine squared of theta times 1/2 plus r. So where is this coming from? If we apply it r equals 0 times, then this goes away. And we go back to this special case at the beginning, this initial state, S. But if we apply it r times, every time we do an application of this Grover iteration, we have another theta. So that means if we do it r times, we're going to have r copies of theta. So every time we do an iteration, we move up theta times. But if we keep going, we're actually going to miss this vertical axis. So we need to know when to stop. When do we stop applying this Grover iteration process? So that is going to happen in the case where this probability is approximately equal to 1. And when is this probability approximately equal to 1? Well, what we need to do is take the inside of this trigonometric function, so the argument of the sine, and we have to set that equal to pi on 2 radians. So let's do that down here. We can set theta times 1/2 plus r approximately equal to pi on 2 radians. So why is it pi on 2 radians? That is this perpendicular angle over here. So what we need is the sine of this argument to be around pi on 2. That corresponds to being vertical, being very close to this vertical axis. And when does this happen? Well, that happens in the case where, let's rearrange this equation, we need r to be equal to pi on 2 theta minus 1/2. So you see what I did? I just moved theta to the other side by dividing, and then I subtracted 1/2. So I'll write this as approximately equal to, because this is just an approximation. And what we need to do is find out what theta is. But we have an expression with theta and n. So we can identify that theta on 2 is equivalent to 1 over the square root of n. And if we take the reciprocal of this, what we can identify is the relationship pi on 2, and then we're going to have root big N on 2 and minus 1/2. But if n is sufficiently large in this approximation, we don't have to worry about this half. So that means we're going to get this final result. R needs to be approximately equal to pi on 4 times the square root of big N. This is how many times we have to apply the Grover iteration. Now, if the square root of big N is not an integer, then we have to take either the floor or the ceiling of this value to get an integer. Because this is an integer up here. We're applying this an integer number of times to the state S. And if we use this relationship over here, we're going to get a probability that is close to 1. And that means if we do this measurement part of the procedure, we're going to measure this with a high probability. And if it turns out we don't measure it, then we just run the procedure again. And if we do it multiple times, on average, we will measure the states that have the highest probability of a measurement. So this is what we've done with Grover's algorithm. We have looked at it from a geometric perspective. We have this geometric visualization. We have this quantum circuit diagram, which summarizes all of the unitary operators that need to be applied. We have written what S is, and we've defined what all of these states are. And we've also defined what all of these unitary operators are. So this part over here is usually called the oracle, and it can be defined in some different ways as well. But with this choice, we're taking this function, which contains information about which state we're looking for, and we use that in a unitary operator, and then we mark that state. So that's what U sub omega does. And then this U sub S, iteratively, when you combine it with U omega, it gets you closer to the vertical axis. So when you perform the measurement with this state over here, after doing it R iterations, you're going to get a very high probability of measuring the state you're searching for. In the next few videos, we're going to see examples of Grover's algorithm.